Now let's continue our discussion on sets by introducing some set operations and talking about subsets and some properties of sets. So we're going to define the union of two sets S and T, written as S this UT, simply to be the set of all elements belonging to either the set S or the set T, or both. So explicitly, this or is not an exclusive or. So symbolically, we can write this definition out. So S union T will simply be the set of all X, such that X is in S or X is in T. Or if I want to be fancy and use logic, this is simply the set of all elements X, such that X is in S or X is in T. So now, previously you should have seen Venn diagrams. So Venn diagrams are simply a way of representing the sets graphically. They are useful for building some intuition, but they are a bit limited in their scope. So let's examine what S union T would look like in terms of Venn diagrams. So explicitly, if I had this set S here, so S is just the set of all things inside this little bubble. And if I had the set T here, so T is just the set of all things inside this bubble, S union T would simply be all of the shaded stuff. So now let's look at a new operation. The intersection of two sets S and T, written S cup T, is simply the set of all elements belonging to the set S and the set T. So symbolically, I can write that the intersection of S and T will be what? Well, it'll simply be the collection of all X, such that X is in the set S and X is in the set T, or using our logical operators, this set will simply be the set of X, such that X is in S and X is in T. In terms of Venn diagrams, what would we expect this to look like? Well, if I drew out my set S and my set T, if X was going to be in both sets, I would simply get this plot here. So here again, T is this set here and everything inside the region bounded by this circle. S is the set here and contains everything bounded by that circle. And the intersection of S and T will simply be this little area here. Okay, so set difference. The difference of two sets S and T, written as S minus T or S backslash T, for this course I'm pretty much uniformly going to use S minus T, is simply the set of all elements that belong to the set S, but do not belong to the set T. So symbolically, we can write that S minus T is equal to, well, what do we think this would be? Well, it's simply going to be the set of all X, such that X is in S and X is not in T. Or, written using our logic operations, it's the set of all X, such that S is in X and X is not in T. Now, if we wanted to, we can go one step further. Previously, we noted that S is not in T could be written using logical operators, so let's expand this out a little bit more. So S minus T would simply be the set of X, such that X is in the set S, and the negation of X is in T. So now, take a moment and draw what you think S minus T would look like. So, what would S minus T look like? Well, I have this set S here, and I have the set T here. S minus T is simply the things that are in S that are not in T, so that'll simply be the shaded area here. Similarly, I could write T minus S, and this will be the set of all the things in T that aren't in S. So notice that S minus T is different than T minus S. So this is a common error that I've seen, and don't mix these up. So now let's revisit the complement of a set. So without explicit mention of the universe U, the complement of a set S, again, is denoted by S bar, and this is going to simply be the set of all elements not in S. Now, how could I write this symbolically? Well, the complement of S will simply be the collection of all X, such that X is not in S. Now, further, sometimes I want to be explicit in what the universe is. So if I'm being explicit in what my universal set is, the complement of a set S whose elements belong in the universal set U is also going to be written by this S bar, and in this case, it's simply going to be the set of all elements in U, but not in S. So in symbols, I can write that the complement of S would simply be this collection of all X in U, such that X is not in S. Now, given that I have an explicit universal set that I'm working with, notice that in terms of the set difference notation, we have that the complement of S is simply U minus S. So for good practice, prove that this statement is true. It's not too hard to do, but it is a bit easier with some of the stuff that I'll define later on in this lecture. So now, graphically, what would the complement of S look like? Well, this is where Venn diagrams start having some limitations, but we can still graphically plot this. So if S is the set of all the things inside this circle, and U is the universal set denoted by everything inside this square, then the complement of S would simply be this area between the circle and the square. So one of the issues that we'll run into when using Venn diagrams is that they don't work particularly well with infinite sets. So here, if, say, the universal set was the set of all integers and S was, say, the set of all even integers, drawing this diagram becomes a little bit problematic, and it's not a formal proof of anything. It's just a visualization technique that you can use to gain some intuition. So in our formal proofs, I do not want to see a Venn diagram, but in your Scratch work, use all the Venn diagrams you want. But do keep in mind that they do have limitations. So now a friendly warning. Notice that the set operations on the left-hand side of these three expressions are not the same thing as the logical operations on the right-hand side. Explicitly, the set operations are applicable to sets, whereas the logical operations on the right-hand side are applicable to logical prepositions. Thus, even though they are similar, they are in fact different operators. That said, you can use the similarities of these two operators to help prove some statements about sets. Okay, now that I've defined all of these operations, let's now go through some examples of using these operations. So let A be the set of all elements of the form 2m, where m is an integer, and let B be the set of all elements of the form 2k plus 1, where k is an integer. What is A union B, and what is A intersect B? So just take a moment to try to do this on your own. So now let's go through the details. What is A union B? Well, by definition, A union B will be the set of all A and Z. So why do I pick Z here? Well, the elements of A and B are both integers, so my domain of discourse should be integers. Now this is the X's and Z's such that there exists a K and Z, such that X is equal to 2K. So this is explicitly saying that X is in this set here, or there exists a K and Z such that X is equal to 2K plus 1. So notice here that I used K and K, whereas earlier I used M and K. It's fine to change the names of these dummy variables to be whatever you want. And since this K in the first parentheses is only defined within the first parentheses, and K in the second parentheses is only defined within the second parentheses, it's fine to reuse the same dummy variable. So I explicitly used K and K just to show you that that's okay. So now let's think about this. So this is the set of all integers such that it's either even or it's odd. Well, that's just the set of all integers. So now what about the intersection? Well, formally, if I write this out, the intersection will simply be the set of all X and Z such that it's even and it's odd. Well, numbers are either even or odd, therefore this is simply the null set. Okay, let's look at another example. Let U be the set of all the integers between 1 and 10. Let C be the set containing 3, 5, 7, 10. And let D be the set containing 1, 3, 6, 7, 8. Calculate C minus D bar. So I'll give you a second to do this. So now, how could you do this? Well, you might think that I could expand this D complement here to be U minus D and then kind of somehow distribute the negative out. That does not work because set plus isn't really defined. So instead, the way to do this is to first calculate D complement. So what is D complement? Well, D complement is simply going to be the set of things that are in U, but not in D. So if I chase that out, 1 is in U, but 1 is in D, so 1's not in D complement. 2 is in U, but 2's not in D, so 2 is in the complement. And I just continue this with all of the elements. So explicitly, 2 is not in D, so 2's in D complement. 4 and 5 are missing between here, so 4 and 5 go in here. 6, 7, 8, and then 9 and 10 are missing, so 9 and 10 go into D complement. So now I simply take the elements of the things that are in C that aren't in D. So to do this, I simply consider each of the elements in C and ask, are those in D? Well, in this case, 3 is in C, but 3 is not in D, therefore 3 will be in C minus D complement. 5 is in C, but 5 is also in D, therefore 5 will not be in C minus D complement. 7 is in C, and it's not in D complement, therefore 7 will be in C minus D complement. And finally, 10 is in C, but it's also in D complement, so it doesn't go into this set. So that's what I have for the examples. If you have questions, ask in office hours on Piazza. So now let's introduce a new definition. Two sets S and T are said to be disjoint whenever S intersects T is the null set. So explicitly, disjoint sets are sets that have nothing in common. So what would this look like via Venn diagrams? Well, it'd simply be S is a set, T is a set. They have nothing in common. Okay, let's look at an example of this. Which of the following pairs of sets are disjoint? So to determine whether or not any of these given pairs of sets are disjoint, I need to ask, do they have any elements in common? Or explicitly, I could compute the intersection. So S is simply the set of all elements of the form 2n, where n is in Z. Well, I know that's the even integers. And T is a set of all things of the form 2n plus 1, where n is Z. Well, I know that's the set of all odd integers. So are these two sets disjoint? Well, yes. The intersection will simply be the null set, so S and T are disjoint. What about this other case? Here, Y is the set of 1, 2, 3, and Z is the set containing the set 1, 2, 3. Are these disjoint or not? These are going to be disjoint. So this set Z is a set containing a set, whereas the set Y is the set containing these three elements 1, 2, 3. And as we know, the set of 1, 2, 3 is different than the set of 1, 2. So now I'm going to introduce the concept of subsets. A set S is called a subset of T, written symbolically as S, this symbol here, T, when every element of S belongs to T. Further, a set S is called a strict or a proper subset of T, written symbolically as S with this cup with the kind of line going through the bottom line T, or simply S cup T, when S is a subset of T and there exists an element of T which does not belong in S. So the difference between this first case here and this second case here is that in this first case, S and T could be the same set even, whereas in the second case, T has to have something that's explicitly not in the set S. So if you want an analogy, this first case is the case where I have, say, A is less than or equal to B, and the second case is where I have A is less than B. But do keep in mind that what I just said is simply an analogy. Now we can further define some stuff. When S is not a subset of T, we can write it symbolically as S is not a subset of T. And when S is a subset of T, we say that T is a superset of S. Finally, when we have that S is a proper subset of T, we can say that T is a strict or a proper subset of S. So this is kind of a lot of notations and definitions to think about. Let's kind of unpack this definition and ask, how can I show whether or not some set is a subset of another? S is a subset of T if and only if, for all X in the universal set or the set of discourse, X is in S implies X is in T. So thus, if I want to show that S is a subset of T, I can simply prove that this statement here is true. So now you can use pretty much any of your proof techniques to prove this statement. So to be a bit more explicit, generally you won't use induction to prove that one set is a subset of another, but you can use proof by cases, proof by contradiction, proof by contrapositive, and of course proof by deduction. So let's look at an example. T is a subset of S and also a proper subset. So what would this look like via Venn diagrams? So pause the video for a second to see what you think it would look like. Okay, so in this case, I would have this big set S that contains elements out here, and this little subset here, T, that's entirely contained within S. And of course, if I threw away this proper subset, then T could be equal to S. Now, another case. For all sets S, the null set is a subset of S. So why would this be true? So pause the video for a second and think about why this could be true. Okay, so why would this be true? Well, explicitly, I want to show that for all X in the universal set, if X is in the null set, then X is in S. So in this case, I know that this statement here is never true since the null set is empty. Therefore, this is saying for all X in U, false implies something. I don't care if it's true or false. I know that that's a true proposition. Thus, in this case, this is vacuously true. Now let's consider a non-trivial case. The natural numbers are a subset of the integers. Well, how would I prove this if I wanted to prove that? Well, you would simply consider some natural number n, and then you'd note that, well, the integers contain that natural number. Therefore, we're done. Further, the integers are a subset of the rational numbers. How would you do this case? Well, we'd simply let z be an integer, and then we'd note that z divided by 1 is of the form of a rational number. Therefore, z is also in Q, and I'm done. And finally, Q is a subset of R. How would I show this? Well, to formally show it, I need a definition of the real numbers, which we're not going to give for this course. So I wouldn't ask you to prove something like this, but we know it's true. And finally, the set of real numbers is a subset of the complex numbers. Well, complex numbers are elements of the form a plus bi. So if I consider some real number, say r, I could simply construct a complex number r plus 0i and show that they're subsets that way. So now I can go one step further. Z is not a subset of the natural numbers. Why? Well, I could say pick -1 or 0. Both of these are integers, but they're not in the natural numbers. And one more example, the set containing 1 pi and e is not a subset of the set containing 1 pi and e squared, because e is not in this set. So to be a bit explicit, if I want to prove that one set S is a subset of another set T, I need to prove this proposition. And if I want to show that a set S is not a subset of T, I need to disprove this proposition. And recall that to prove this proposition, I need to show that it holds for all X. And to disprove this proposition, I need to simply find a counterexample. If you have any questions on this process or any particular examples you want me to go over, you can ask on Piazza or in office hours. So now that I've defined set equality and subsets of sets, I can build a very useful proposition. Two sets S and T are equal if and only if S is a subset of T and T is a subset of S. So by analogy, this is similar to saying that two real numbers, say A and B, are equal if and only if A is less than or equal to B and B is less than or equal to A. So notice here that this is an analogy. It's not exact, but this is the basic idea. So now, why would I want this theorem? Well, it turns out that showing that two sets are equal in a lot of contexts can be really difficult. But on the other hand, showing that one set is a subset of another is relatively easy. All I have to do is prove this proposition here. So how can I prove this? Well, let's go through the proof. Since this is an if and only if proof, recall that I have to show two directions. I have to show that if the two sets are equal, then this proposition here holds. And I have to show that if they're subsets of each other, then they're equal. Now, it turns out that for this case, I can prove both directions at the same time. So without further ado, let's prove this statement. So by deduction, I know A is equal to B if and only if what? Well, A is equal to B if and only if X is an element of A, if and only if X is an element of B. So the right-hand side here is explicitly saying that if X is an element of A, then X has to be an element of B, and if X is an element of B, then X has to be an element of A. So if you were writing a formal proof and wanted to justify this step, you could say by the definition of set equality. So next we're going to take these two statements and expand them out. Well, how can I do that? Well, I know that statement A, if and only if statement B, is equivalent to statement A implies B, and statement A is implied by B. So here, I'm just expanding this out by the definition of if and only if. So here, if I wanted to give a justification for this step, I would say the definition of if and only if. So now notice that here I have an and up here I wanted to prove an and. So now I'm starting to make progress towards the solution. Now the next thing I need to really do is try to tie these statements in parentheses somehow to these statements. Well, if whenever X is an element of A, if that implies that X is an element of B, this is the statement that A is a subset of B. If on the other hand, whenever X is an element of B, that implies X is an element of A, that's the definition of B being a subset of A. Thus, this statement here is equivalent to the statement that A is a subset of B and B is a subset of A, which is what I wanted to prove. So I just now noticed that I used S here and I used A here. This is not a problem for this proof, but it would be a bit more cleaner if I was consistent with using A and S. So I apologize for the copy-paste error and the fact that I'm leaving it in here. I will fix it on the lecture slides that I upload though. And ta-da, it's fixed. Okay, so let's look at another proposition. For sets S and T, S is equal to T if and only if the union of S and T is equal to the intersection of S and T. Now, this is the type of question I could potentially ask you on an assignment, midterm, or final. So do pay attention to the proof techniques that I use here. So like on the previous slide, Here I have an if and only if statement, so there's two directions to prove. Unlike the previous slide though, it's easier to prove the forward direction and then the backwards direction rather than trying to get a series of logical deductions like this, where I have if and only ifs between each statement. Okay, so let's jump right in. So now, if I'm proving the forward direction, I want to start by assuming that s is equal to t, or t is equal to s, and then I want to show that these two sets are equal. Well, as I said previously, proving directly that two sets are equal can be tedious or even hard or even impossible. So for this problem, I'm going to show that the intersection is a subset of the union, and the union is a subset of the intersection. So explicitly, I'm using the proposition on the previous slide. So let's jump right in. Well, let x be an element of the intersection be given. So this is some arbitrary element of the intersection. I don't know what it is, but it's in the intersection. Well, let's unpack this definition a bit. Since x is in the intersection of t and s, by definition, x is in s and x is in t. So now I somehow need to use this fact to show that x is going to be in the union. Well, this is pretty trivial. Thus, by definition, x is in s union t, right? Since x is in s, it's in the union. I don't even need the fact that x is in t. Or vice versa, I could say since x is in t, it's in the union, and I don't even need the fact that x is in s. So now, since x is in the union, it follows that the intersection is a subset of the union. So that is done for this case. So we are done for this statement here. So now we also need to show that this statement is true. So how do I do this? I first let x be an arbitrary element of the union. Again, I don't know what x is. I just know it's in the union. Well, how does this help? Since x is in the union, by definition, x is either in s or t, or it could be in both conceivably. Now, since s is equal to t, x must be an element of both s and t, right? Since, say, if x was in s, then since s is equal to t, then it automatically is in t, or vice versa. So notice here that I'm using the fact that s is equal to t for this bulletin point, but I did not use the fact that s is equal to t for the previous bullet point. This is explicitly because the intersection is always a subset of the union, no matter what the sets are, but the union is only a subset of the intersection when s is equal to t. Okay, back to our proof in question. Since x must be an element of both s and t, what does that tell me? Well, by definition, x is now going to be in the intersection of s and t. Therefore, I've now proven that the union is a subset of the intersection. And this is precisely what I wanted to prove for the forward direction, so I am now done. Now, on the converse direction, let s and t be two sets such that the intersection is equal to the union. Right? I'm starting by assuming that this hypothesis here holds. Now, my goal is to show that s has to be equal to t. How can I do this? Well, it turns out that proof by contradiction is a good method. So assume for the sake of contradiction that s is not equal to t. Now we're going to use our assumption that the union is equal to the intersection to contradict this fact. So what does our assumption tell us? Well, thus, there either has to be some t in capital T such that t is not an s, or some s in the set S such that s is not in t. So technically we have two cases here, but since I can swap the order of s and t in my proposition, it doesn't matter which case I use. So this is a very good spot to use without loss of generality. So without loss of generality, assume that there is some t in t such that t is in s. So now what if there existed some element t in t such that t is not an element of s? Well, it would follow that t would be in the union of s and t, but at the same time, by definition, t would not be in the intersection of s and t. Now, originally, I let s and t be set such that the intersection equaled the union, and now, with this assumption, I've shown that there is an element in the union that is not in the intersection. This is a contradiction that the union is equal to the intersection. Thus, our original assumption that s was not equal to t is false, and therefore s is equal to t. Now, before I look at the assigned reading, let's take a step back and look at the structure of this proof. So since it was an if and only if proof, I had to prove two directions. So the first direction, the second direction. And within each of these directions, in the converse direction, I used proof by contradiction, whereas in the forward direction, I used a direct proof to prove that two different statements were true, and one of these statements that I proved did not explicitly need my hypothesis because it's true for all sets. So now it's not terribly uncommon to have proofs where I use multiple proof techniques and have this kind of compound structure that I have in this proof. So just keep that in mind throughout your work. Okay, so now for assigned reading. I want you to read claims 14 through 17 in the text with a focus on their proofs. Now, in your homework, you can freely use any of the properties in these claims. So you should commit to memory these properties outlined in claims 14 through 17. And in addition, knowledge of the proofs for claims 14 through 17 can help you to prove other propositions that I might ask you to prove on, say, an assignment, a midterm, or a final. So these are very good practice problems with proofs, and I highly suggest you do this assigned reading. You can now understand this meme. As always, if you have any questions, ask in Piazza or office hours, and have a wonderful weekend.